I'd like to welcome everybody back, and hopefully you were able to join us for this morning's session. This is the afternoon session of the spring webinar that we're running in place of the planned event in Nottingham, obviously due to the restrictions. There is hope that we actually may get back to face-to-face meetings in time for the AGM at the end of October, the Institute of Physics. So that's, at the moment, is our plan. But at the moment, we're continuing our webinars for everybody to enjoy. Okay, so this afternoon we've got Professor Clive Tadhunter, who's the Professor of Astronomy and Professor of Astrophysics up at Sheffield University. Clive initially studied at St Andrews, moving to Sussex for his doctorate, and then had postdoctorate positions at St Andrews again, the European Southern Observatory, and at Cambridge as well, before moving to Sheffield as head of astronomy, where he's the Professor of Astrophysics now. His talk this afternoon, as you'll see on the screen, quasars, black holes, and the future of the Milky Way. So without further ado, if I can pass you over to Clive Tadhunter. Thank you very much.
Okay, thank you very much for your introduction. So I'm going to be talking about quasars, which are the most luminous objects in the universe. You'd have heard something about them from Christian Knigger's talk this morning. I'm going to talk about how they're powered by black holes, how we find them, which turns out to be very challenging, and how they may be involved in the future of our own Milky Way. And this is the field that's really benefited over the last 30 years or so from technological advances, the sort of advances that affect all our lives. The fact that I can present this talk on a laptop across the web, all these amazing technologies we have that have a direct impact on observational astronomy, both professional and amateur, and particularly on this field. So if we start with the Milky Way, we look up on a clear night in the countryside, dark skies, we see this dusky band crossing the sky, and it's a big pile of stars. It's 400 billion stars like the sun, and that's the system we call our Milky Way. Now, of course, if we look out in space, there are very many other separate island universes, all with their own hundreds of billions of stars, many other galaxies out there in space. In fact, there are as many galaxies in the visible universe, about 400 billion, as there are stars in the Milky Way. And of course, they come in all shapes and sizes. And one of the things we can do is classify them. And the main way we classify them is to use this tuning fork diagram that was originally developed by Edwin Hubble back in the 1920s. And on the handle, if you like, of the tuning fork, we have elliptical galaxies. They're just round or elliptical shapes, quite featureless galaxies. And then we have the two tines of the tuning forks. We have the ordinary spiraled, unbarred spirals at the top, and we have barred spirals at the bottom. And all these systems comprise hundreds of billions of stars. And if we were to fly outside the Milky Way to try and get a clearer view of it, our galaxy would look something like this SBC galaxy at the bottom right hand of the Hubble tuning fork diagram. And of course, the reason we do such classification is to try and find underlying patterns that might tell us about the evolution and origin of such systems as galaxies. And there's a lot of uncertainties about how galaxies evolve. Do ellipticals evolve into spirals or vice versa? And of course, one way we can study this is by looking at images and studying the morphologies and the detailed structures. But from images alone, we only get limited information, and we need to use other techniques to get the full picture. And one other very important technique that we use in astronomy is spectroscopy. And basically what we're doing with spectroscopy is to put the light through a prism or diffraction grating and look at the different intensities of different wavelengths of light. And if we do that, we see the familiar colors of the rainbow that we get from a prism or diffraction grating. But overlaid on that, we see sharp features. They could be light emission features or dark absorption features. And these are the fingerprints of the elements. So individual atoms comprise a nucleus with electrons around them. The electrons can have different energy states. And as the electrons jump between the energy states, they emit particular wavelengths of light. And because each atom has its own unique set of energy levels, the sharp emission or absorption features we see are unique to that element. So hydrogen has a different set of sharp features to helium, oxygen, neon, etc. So one of the fascinating things is that if we look at a galaxy halfway across the universe, many megaparsecs away, we can identify particular elements. And it turns out we can identify the same elements that we find on Earth and that we're made of. But the other thing we can do with spectroscopy is measure how fast things are moving. And this is very important. And this is based on the Doppler effect. So if an object's moving away from us, as shown at top, as we observe it, then the light wave is stretched out, because as it's emitting the light wave, it's moving away from us. And longer wavelengths of light means redder light. So if we see a sharp feature in our spectrum, it's shifted to the red if the object's moving away from us, and that's a red shift. On the other hand, if the object's moving towards us, the wave gets scrunched up. So the object's moving towards us as it emits the light, we get shorter wavelengths, that's bluer light, and the feature's blue shifted. And so we can use this property of blue or red shifted of these sharp features, these fingerprints of the elements, to measure the velocities of things, how fast things are moving. And we may have situations where instead of seeing one cloud or star moving away from us or towards us, we have some kind of ensemble of stars, a cluster of stars or clouds, and some might be moving towards us and some away from us. So we simultaneously get a red shift and a blue shift, and that broadens the feature. So we see a broad feature. And it was using the technique of spectroscopy that it was found that something pretty extraordinary is going on in the center of some galaxies. And this was first studied systematically by Carl Seifert in the middle of the Second War, and he published a paper in 1943. And what he did was that he looked at images of certain galaxies, and he noticed that some of them had very bright cores. So you see a set of images on the left there. So the short exposure is shown at the top, and in a short exposure, the galaxy looks like a point source. It looks like a star. And it's only when we take a longer exposure that we see the underlying galaxy at the bottom. So a Seifert galaxy, these are now called Seifert galaxies in honor of Seifert, is a galaxy in which the nucleus is about as bright as all the hundreds of billions of stars in the host galaxy. So that's one important feature of Seifert galaxies. But the other thing that Seifert did was that he took spectra of the galaxies. So you can see spectra of some Seifert galaxies on the right. So this is intensity against wavelength. And you see all these sharp features, which are due to elements, the characteristic fingerprints of the elements in the distant galaxies. So we see features due to oxygen, iron, nitrogen. And the thing is that we see very high states of ionization. So we see iron 7, that's iron with 6 electrons stripped off of it. We see neon 5. We see very high states of ionization. And what's more, what you notice is that some of these features are very broad. And on the basis of the Doppler effect, we deduced that means that the gas is moving around at thousands of kilometers a second. And overall, these observations provide evidence for something very energetic going on in the centers of some galaxies. And around this time, astronomers also started to look at the universe with other wavelengths of light. And in particular, in the 1930s and 40s, the radio window was opened up. So this is looking at much longer wavelengths of light than we can see with our eyes. It's a sort of the sort of radiation we pick up on our radios. And certain discrete radio sources were discovered in the sky. And this is a radio image of one of them called Cygnus A, because it's the brightest radio source in the constellation of Cygnus. And what we find is structures that look extraordinarily different from the galaxies we're familiar with. Instead of the spiral or elliptical galaxies we see at optical wavelengths, we see these giant double lobes, radio emission. And we believe that these lobes are full of particles that are moving relativistically close to the speed of light, spiraling in a magnetic field, and emitting radiation that happens to come out at radio wavelengths. And the other thing about these structures is that they're very large. So they're about 10 to 100 times larger than the galaxy that we'd see at optical wavelengths. And the other thing you'll notice from this is that the lobes, these giant lobes, are connected to the nucleus, this dot in the center, by exquisite jets. So what we got here are natural particle accelerators. And in fact, the jets of Cygnus A are about 10 to the 25 times more powerful than the Large Hadron Collider, but they're produced naturally in this system. So these systems that we call radio galaxies are extraordinarily powerful, and Cygnus A at radio wavelengths is 1 million times more powerful than the Milky Way. Now, if we image these radio sources at optical wavelength, what we usually find is galaxies. They're elliptical galaxies usually underlying the radio emission. But at the position of some of them, it was found back in the early 1960s that instead of a galaxy, we see something that looks like a star. So on the left here, you see an image of one of these sources, and it's a heavily saturated image that's point-like. And these are quasi-stellar, so they're star-like. They're not exactly like stars because we see some extended structure. So this one, for example, has a jet pointing out of it. So these are quasi-stellar objects. That's where the term quasar comes from. And the thing about them is that initially they were thought to be some unusual type of star in the Milky Way. But then Martin Schmidt in the early 1960s took a spectrum of one of them, and the spectrum shown on the right. And what he found was that there were very strong emission lines due to hydrogen. And so this looks like the spectrum of one of the galaxies studied by Seifert. But the features are all shifted. They're red-shifted by an enormous amount. So the redshift is 0.158. And if we interpret that in terms of the expansion of the universe, the further away an object is, the higher its redshift, then this object's a long way away. And if we know its distance, we can work out its luminosity, the radiation it emits in all directions. And it turns out that this object, 3C273, is about 100 times more luminous than all the stars in a galaxy, like all the hundreds of billions of stars in a galaxy like the Milky Way. And since the discovery of this object, many tens of thousands of quasars have been discovered, and they've got luminosities between 10 and 10,000 times the integrated light of all the stars in the Milky Way. So these are the most luminous objects in the universe. So if we summarize the properties of these active nuclei, they have certain key characteristics that they all have in common. They're quite a diverse phenomenon, as you saw from Christian Knigger's talk this morning, but they have certain key characteristics in common. One is that they have extraordinarily large luminosities. So between 1, in the case of Seifert galaxies, up to 10,000 in the case of quasars, times the light of all the stars in a typical galaxy like the Milky Way. We know from their variability that the size over which all this power is generated is very small. The size of the region is very small. It's typically solar system size, less than 1 light year, less than the distance between the sun and the nearest star. And they have large lifetimes too. By studying their radio emission, we can deduce that these sources last for between 1 and 100 million years. So they're not just a flash in a pan like a supernova. A supernova can be bright when it goes off, an exploding star, but a supernova fades rapidly on a time scale of months. These objects, these active galactic nuclei, can last for millions of years. And then they have also the ability to produce highly collimated jets. So the problem, how we generate this extraordinary luminosity, amount of power from such a small volume over such a long time period. And the most likely solution is that we're seeing the accretion of material to the close vicinities of supermassive black holes. So because it's an important part of my talk, I should explain what a black hole is. And I think to understand black holes, it's useful to think in terms of escape velocity. So if you throw something up, it will come down. If you throw it a bit faster, it will go higher up and then it will come down again. If you throw it fast enough and you give it enough kinetic energy, then it could escape the Earth. And that velocity for the Earth is about 11 kilometers a second. The point is that if we shrink the body, it could be the Earth, it could be a star. If we shrink it but keep its mass the same, the surface gravity increases. So the surface gravity shown by the arrow, and that means that the escape velocity increases. So if you shrink the object, the escape velocity increases. And if you shrink it enough, eventually the escape velocity becomes the speed of light. And since nothing can travel faster than the speed of light, that means that nothing can escape the velocity, the body. So black holes are objects that are so condensed and the surface gravity so strong that nothing can escape, not even light. So the escape velocity is greater than the speed of light. And you might ask, well, how small would you have to make the Earth for it to be a black hole? Well, the answer is you'd have to make it this big, the size of a squash ball, about 1 centimeter raised. You'd have to crush all the rock in the Earth to ball that size to make it into a black hole. So, so black holes are very condensed states of matter, extraordinary objects. Now, you may think of black holes as being a modern concept, but the idea actually goes back a couple of centuries to the late 18th century. It was first proposed by John Michell. He was a polymath. He was actually also the father of modern seismology. He made contributions to lots of different fields of science, but he was the first to really suggest this idea of black holes. The idea was then picked up a bit later by Laplace, famous French mathematician, scientist. But of course, the mathematical foundations of black holes were laid in the early 20th century, the first half of the 20th century, with the development of general relativity. So really, we need general relativity rather than Newtonian gravity to explain the strong gravity around black holes. And of course, those theories initially developed by Albert Einstein in the early 20th century, about 100 years ago. So black holes, we think that they generate all this power we see in quasars. But you may think, well, a black hole is so condensed and massive, its gravity is so strong, nothing could escape, not even light. So how do we get all this luminosity, all this light that we see? Well, we believe that the light is generated by the conversion of gravitational energy into heat and light as material falls in close to the black hole. And I think a good analogy to this is a waterfall. So in a waterfall, water starts at the top of the waterfall, it accelerates under gravity, so it picks up kinetic energy, half mv squared. And when it hits the bottom, this energy is released. And some of it, in the case of waterfall, will be released as sound waves that we can hear, but some of it will be released as heat. And so if you measure the temperature at the bottom of the waterfall, it'll be slightly higher than at the top. And this is the conversion of gravitational energy into heat. And it's similar with black holes. So material can fall into the potential well of the black hole, fall close to it. It's got a very long way to fall, and it could fall onto the accretion disk, some kind of accretion disk around the black hole. And then there's a release of gravitational energy into heat. And in this case, not sound waves, but light. And the point is that this is an incredibly efficient process. So the efficiency of energy generation is about 10 times that of the nuclear fusion that makes stars shine. So it's a very efficient process. And that means that we can generate an enormous amount of energy from a small volume. But we do require massive, supermassive black holes to generate enough energy. And they'd have to have masses greater than about 10 to the 7 or 10 million solar masses to generate quasar luminosities. So that's the idea. Conversion of gravitational energy into heat of light in the deep potential wells of black holes. But of course, we'd like to find evidence that galaxies actually do have black holes in their cores. So what's the observational evidence for supermassive black holes in the centers of galaxies? Well, it's challenging. It's actually challenging to find black holes, and that's because they don't shine directly like stars, and they're also tiny. So they're actually difficult to find. And there are three methods we might use to find them. One is the heating effect. So as I just said, stuff being accreted by the black hole before it actually enters the black hole, crosses the event horizon, could get heated up by this conversion of gravitational energy into heat and light. And that is actually what we see in quasars. So quasars actually provide indirect evidence for supermassive black holes in the centers of galaxies. But we'd like to have more direct evidence of black holes than just the quasars themselves. And one method we might use, and I think this was actually realized by Michel back in the late 18th century, is that particles moving close to black holes would be moving very fast. If they're close enough in, the gravity of the black hole is very strong, and we can see very rapid motions of test particles. So we can look for those very high velocities as evidence for black holes. But the most direct evidence would be provided by actually imaging the black hole, or specifically looking for the silhouette of the black hole against the material that's being accreted. So we can use these techniques. So as I say, we've already covered quasars, that's a heating effect. What about velocities? So the idea here is that if a particle is close enough in, because of the strong gravity, you get a very, very high velocity, and you can detect that observationally. The problem is you have to get really close in, because black holes are so small that you have to get to very small radii for the gravitational effect of the black hole to dominate. If you're on larger scales, then you have all the stars and gas in the galaxy, and they're more massive than the black hole, and they dominate the gravity. So you have to get into the central 100 parsecs or so, really close to the central black hole. And this is a problem because you require high spatial resolution. And it's a problem with ground-based observations, because from the ground, images of stars and galaxies are blurred by the turbulence in the Earth's atmosphere, what we call atmospheric seeing. So if we look at an image of a star cluster with the best ground-based resolution with conventional techniques, we get this image. Everything looks blurry. And this is because of the turbulence in the atmosphere distorting things and blurring our images. It doesn't matter how big we make our telescope, unless we use special techniques like adaptive optics, the images are blurry because of the Earth's atmosphere. And this is related to the phenomenon of twinkling of stars that you see close to the horizon. That effect of the atmosphere also blurs the images. But what we can do is launch our telescope in space. And of course, that's what the Hubble Space Telescope is. So the Hubble Space Telescope has got superb optics, and it's in space. And so if we image the same star cluster, this is exactly the same field on the sky with a Hubble Space Telescope, we get much higher resolution. So with the Hubble Space Telescope, we have about 10 times the spatial resolution that we have from the ground, because we don't have the distorting effects of the Earth's atmosphere, and we can see all the detail. We can see that this is a star, and this is just what we need to look for black holes. And this is what astronomers have done over the last 25 years or so. And one of the first objects they looked at was the giant elliptical galaxy at the center of the Virgo cluster, M87, Messier 87. And there are already signs that this object has got a black hole in it, because we can see this jet coming out. So there's some low-level activity in this object. But if we look closely at the center, what we see is this swirling disk of gas. And this is an image in the light of singly ionized oxygen. And so we see this swirling disk of gas in the center. And the thing about this is that if we can measure the velocities of this disk, then we can potentially look for the high velocities that we'd expect for a black hole. And this is exactly what's been done. So what astronomers have done is that they put their spectrograph slit, shown on the left, across the disk, and then taken a spectrum shown on the right. So in the right-hand image, what you see is what we call a long-slit spectrum. It's got wavelength along the bottom axis, left to right, and spatial position top to bottom. So each row going up this spectrum is a separate region across the galaxy. It's a separate spectrum. And this has been observed in the light of singly ionized oxygen, oxygen 2 as we call it. And this bright feature is the sharp feature due to the ionized oxygen. And what we see is that if we go from this side, one side of the disk, the feature is shifted to the blue. It's got a shorter wavelength. And if we go to the other side of the nucleus in the disk, the feature is shifted to the red. So we see blue shift, red shift, and this is characteristic of a rotating disk. And the velocities are very high. They're plus or minus 600 kilometers a second. So That's much higher, for example, than the sun going around the center of the Milky Way. That's about 200 kilometers a second. So very high velocities, very close into the center of M87. If you measure the mass, it's between 3 and 7 times 10 to the 9 billion solar masses. And what's really important about this is that the mass we measure for the center of M87 is about 30 times greater than can be accounted for by the visible stars and gas, because you have stars and gas which have some emission in the center, but the mass of those stars and gas can't account for this large mass we measure. So that's excellent evidence for something dark and massive there, which could be a supermassive black hole. Here's another example. This is an elliptical galaxy with dust lanes across it, and the astronomers have put their slit across the center, across the nucleus. And again, what we see, this is wavelength left to right and position top to bottom. Low velocities at large distances from the center. So this edge of the slit here. But as we get towards the center, we suddenly see a very large redshift, longer wavelengths of light in this, this emission feature. I think it's oxygen 2 again. And then just slightly further across the other side of the nucleus, a very strong blue shift. So again, this is a sign of redshifted emission going away from us on one side of this, blue shifted on the other, very high velocities, many hundreds of kilometers a second. And again, evidence for a very large mass there, about 1.5 times 10 to the 9, 1.5 billion solar masses in the center of the galaxy. Again, much larger than we expect from the light we see there. And in fact, if we look at most massive galaxies close to the Milky Way that we can look at in detail, we find evidence like this for supermassive black holes in their cores. But of course, the object we're really interested in is the Milky Way, our own Milky Way system. Unfortunately, if we look towards the center of the Milky Way at optical wavelengths, the sort of wavelengths of light we can see with our eyes, then we don't get a very clear view. And that's because the disk of our Milky Way, which we're in, is full of gas and dust, and that absorbs optical wavelengths. And so we can't actually see the center of the Milky Way directly at optical wavelengths because it suffers, I think, 30 magnitudes of extinction. But what we can do is that we can take an infrared image of the center of the Milky Way, because infrared light penetrates the dust and gas. And so this is an infrared image, and what we find there is a cluster of stars, a compact cluster of stars on a scale much smaller than a parsec. And the group that took this image, led by Reinhard Genzel in Germany, have not just taken one image, they've taken a whole series so they can make a movie of the motion of the stars in the center of the Milky Way. So I'll set that going. And what you notice is that the stars close to the center, the galactic centers, the real center of the galaxy, are moving much faster than those further out. And I should say, to detect these motions at all is extraordinary, because we can easily measure the velocities of things using the Doppler effect, using spectroscopy. That's along our line of sight. But to measure the motions tangential to our line of sight is very challenging because the angles are so small. So to be able to detect the motions of the stars in the center of the Milky Way, which is a long way away, it's 8 kiloparsecs away, is extraordinary. And it means that the stars must be moving very fast, and actually they're moving at thousands of kilometers a second. Anyway, so what we can see is the stars in the center are moving much faster than those further out. And then if we zoom in, we can actually track the orbits of individual stars around the center of the Milky Way. And what's extraordinary is that they're moving very fast, to say thousands of kilometers a second, but we can't see the thing that they're orbiting around. It's dark. And so this is excellent evidence for a black hole in the center of the Milky Way. And the mass that's measured by studying the orbits of these stars and how fast they're moving is about 4 million solar masses. And for me, this is one of the science results of the last 30 years, the detection of these motions and the measurement of the mass of the black hole in the center of the Milky Way. And it's some of the best evidence we have for a supermassive black hole in any galaxy, and it's in the center of our own galaxy. And Reinhard Genzel, who led the group that did this work, had a share in the Nobel Prize for Physics last year for doing this work. So extraordinary results. So that's the Milky Way. And as I say, most large galaxies close to the Milky Way have supermassive black holes in them. But most of those galaxies are not active. In fact, only a tiny fraction of nearby galaxies have quasars in them, much less than 1%. But what we'd like to do is actually see whether quasars have black holes in them, because we believe that that's the power source for quasars. For quasars, though, it's challenging to look for the black holes directly. And that's because we're kind of dazzled by all the light of the quasar. There is a galaxy underneath this quasar, 3C273, but it's very hard to see because the quasar is 100 times brighter. So we're kind of dazzled by that. And it's difficult to see the little disks of gas and stars that we might measure to measure the large velocities. Fortunately, in some cases, in this case here, Cygnus A, this object with the radio jets that I showed you earlier, the quasar is actually blocked off at optical wavelengths. So like we can't see towards the center of the Milky Way at optical wavelengths because of the gas and dust in the way, in Cygnus A, we think there's a quasar there because it's got these extraordinary jets and all sorts of radiation at other wavelengths. But the direct optical light of the quasar is blocked off by the gas and dust and the disk in the middle. And if we look at the center, we see signs, this is the central galaxy, of a little disk in the center. And so this allows us to try and detect the supermassive black hole in this quasar. And this is what we did about 20 years ago, my group in Sheffield. We used the Hubble Space Telescope to measure the velocities of the gas in the disk around the center of Cygnus A. And we found red-shifted velocities on one side and blue-shifted velocities on the other side. And the velocities are very large, several hundred kilometers a second. And we measured a mass of a few billion solar masses for whatever's in the center here. And again, that was much more massive than we'd expect from the starlight. So this remains actually the most direct evidence we have for a supermassive black hole in an object with a quasar. But as I say, most galaxies have black holes in their cores, but most of them aren't active. So the Milky Way has got a supermassive black hole. Most nearby large galaxies we know have got black holes in their cores, but they're not quasars. Quasars are very rare. They're much less than 1% of galaxies appear as quasars. So why is it that some galaxies are incredibly luminous and appear as quasars, but others we don't see anything? Well, we believe that this is actually related to the accretion of material, that we only see all the heat and light, the conversion of gravitational energy into heat and light, when material is being accreted by the black holes. The black holes themselves don't shine directly. And actually the luminosity that we see depends on the rate at which mass is accreted by the black holes. The more kilograms per second that are falling into the black hole, the more heat and light we generate. So what we think is going on with quasars is that they're accreting an unusually large amount of material, accreting material at a very high rate. But then there's a question about why. Why are quasars accreting so much more material in their nuclei than other galaxies? Well, we believe that an important mechanism for triggering quasars is galaxy mergers. So we know from imaging in the local universe that some galaxies are merging together. So this is an example. This is the antennae. On the left, you see a wide field image. And when we have a collision between two galaxies, all the structures get distorted. They don't look like spirals. They don't look like ellipticals. We see these tidal features, these tails, and we get lots of star formation. So the image on the right is beautiful HST, Hubble Space Telescope image, and we see that there's lots of star formation. But the other thing that happens, as well as star formation due to the high gas densities, is that material gets pushed towards the centers of the galaxies. So we get radial motion. Instead of being on circular orbits, the gas is moving radially, and it can be pushed towards the central regions of the galaxies and accreted by the supermassive black holes. And I've got this simulation. This is a simulation of a galaxy merger that shows this process. So we have two spiral galaxies here, and this shows the gas in the spiral galaxies. So there could be spiral galaxies like the Milky Way. They merge together. Look at the time scale. This is mega years. This is millions of years. So we're talking about very long time scales. That's their first collision, and then they pull apart again. But the thing to notice is that instead of moving on circular orbits, you can see that the gas is actually raining in to these galaxies. It's got radial motion, so it can be accreted by the black holes in the centers of the galaxies. And so the quasars in these galaxies switch on, and then what you notice is that the gas gets blasted out, and that's because the quasars have such intense radiation and winds that they blast the gas out. And then eventually the two black holes merge together and you get more accretion, and it's like an explosion. The rest of the galaxy, gas in the galaxy gets blasted out by the outflow. So the point is that quasars are triggered in such mergers, but once they're triggered, they have an enormous effect on the remnant. They blast out the gas, and that means that there can be no further star formation. So there's an enormous feedback effect, if you like, of the quasars on the host galaxies. So what's the evidence that quasars are triggered by mergers? The problem is that because the nuclei is so bright, and we're kind of dazzled by the nuclei, it's difficult to see the underlying galaxies. But the Hubble Space Telescope is useful for this because it can more easily separate the nucleus from the host galaxy. From the ground, it's difficult because everything's blurry. But with HST, we've got some hope of seeing the underlying galaxy. So this is an image of a quasar that was taken with the Hubble Space Telescope. And if you look at the image on the right, you can see the bright quasar nucleus, but you can see the structures of the underlying host galaxy. And it doesn't look like a spiral. It doesn't look like an elliptical. You can see tidal tails. So that's clear evidence that this quasar is being triggered in a merger. The trouble is that even with the Hubble Space Telescope, if we look at quasars directly, we can only do this for a few systems, and the point source of the quasar makes it very difficult to see the underlying galaxy. So one project we've been undertaking in Sheffield over the last decade is to look at quasars in which the quasar is obscured at optical wavelengths. So what that means is that the disk of gas and dust in the galaxy is at such an orientation that it blocks out the direct light of the quasar. We know there's a quasar there because we can see the radio emission, X-ray emission, all that sort of thing. But at optical wavelengths, the sort of light we can see with our eyes, the direct light of the quasar is blocked off because there's a disk of gas and dust in the way. So it's like Cygnus A I showed you earlier, like the center of our galaxy, we can't see through to the nucleus. And the advantage of this is that we can then study the detailed structures of the underlying galaxies. And what we find is that we've now looked at several samples of quasars with obscure nuclei, is that a very high proportion of them, somewhere between 60 and 95% of them, depending on the sample, show evidence for these tidal features, tidal tails and things like that, and shells that are characteristic of mergers. And we see a much higher rate of tidal features in the quasar host than control samples of non-active galaxies of similar mass. It's less than 30% in those. So this provides very clear evidence that quasars are triggered in major galaxy mergers. Okay, so I've talked about the velocity technique to find quasars, and I've talked about the heating that we get, the heating effect we see in quasars. But the most direct evidence for quasars would be provided by direct imaging, looking for the silhouette of the black hole against the accreting material. The problem with using direct imaging to detect supermassive black holes is that we require about 3,000 times better resolution than the Hubble Space Telescope, even for the largest black holes. And so resolution is a challenge in astronomy. The resolution of a telescope roughly goes as the ratio of the wavelength to the diameter of the telescope. So we get the highest resolution, that's the smallest delta theta, the smallest angle that objects that can be separated by, so that we can resolve them. We get the best resolution, smallest delta theta in this equation, if the wavelength's small or the diameter of the telescope is large. So we'd like to work at short wavelengths with a large diameter telescope. This is a problem at optical wavelengths, though, because the atmosphere is very unstable and we get this blurring effect seeing, and it's actually difficult to do high resolution spectroscopy at optical wavelengths from the ground. We could think of launching our telescope into space, but we'd have to make it 3,000 times bigger than the Hubble Space Telescope to get sufficient resolution. So that's not feasible. So what we need is to work at longer wavelengths where the atmosphere distorts things less. So we're talking about radio wavelengths and microwave wavelengths, but also we need a large diameter. And the technique we use is interferometry. If we just took a single dish in the radio, because the wavelength's so long, the lambda's so long, we don't get a very high resolution. So we really need a large D to compensate for the large L, for the large lambda resolution. And so instead of using a single dish, what astronomers do is they interfere the signals from large numbers of radio, can be 2 radio telescopes up to say 30 radio telescopes. They interfere the signals of widely separated telescopes. And the point is that here, D is not the diameter of an individual dish, it's the maximum separation between the dishes. So if we can separate the dishes by kilometers, hundreds of kilometers, or thousands of kilometers, then we can get very high resolutions. In fact, we can get higher resolutions and achieve the shorter optical wavelengths. And this is exactly what the Event Horizon Telescope collaboration have done over the last, the bright in the image, the lighter colors are the material being accreted by the black hole. And the black hole itself is the silhouette in the center. It doesn't shine directly, but we see it as a silhouette. And this is the best evidence we have for a black hole in any galaxy, including the Milky Way. So extraordinary result that's come out over the last few years. We can now directly image the silhouettes of black holes, incredibly technically challenging. So to finish my talk, what I want to talk about is the fate of the Milky Way and whether quasars and black holes will be important in the Milky Way in the future. Now, if we look at the Milky Way, it's a beautiful optical image. We see the stars, we see evidence, we see the dust lanes, there's lots of gas and dust there. And one question I'm often asked is, if there's a black hole, there's this 4 million solar mass black hole in the center of the Milky Way, why isn't it just sucking in all the gas? And if it sucks in all the gas and dust, then why don't we see a quasar? Because we get a high accretion rate and we'd expect to see a quasar because of the conversion of gravitational energy into heat and light. So why isn't there a strong gravity of the black hole in the center sucking all the gas in so that we see a quasar? Well, the point is that all the gas and stars, or most of the gas and stars in the center of the Milky Way, is moving on circular orbits. So just like the Earth's going around the sun's going around the center of the Milky Way, the gas and dust in the center of the Milky Way is on circular orbits, and it's moving fast enough to not fall in to the black hole. It's on stable orbits. So unless something perturbs that gas and the stars, then they will stay on the circular orbits, and there won't be a very high accretion rate onto the black hole in the center of the Milky Way, and the black hole won't be active and we won't see a quasar. But there is a question actually about whether the Milky Way will ever be a quasar. And the answer to that is probably yes. And the reason for that is that if we look at the closest large galaxy, that's the Andromeda spiral galaxy, which I'm sure many of you have seen with the naked eye, with your peripheral vision. You can see this one with the naked eye. The closest large spiral galaxy. It turns out that it's coming directly towards us at about 300 kilometers a second. So we know from the Doppler shift, it's coming towards us at 300 kilometers a second. From Hubble Space Telescope imaging, we know that it's not moving very much sideways, so it's coming directly towards us. And in fact, it will hit the Milky Way and merge with it in about 6 billion years. So we don't have to be worried now, but in 6 billion years, we're going to have this collision. And there's some beautiful simulations showing what this collision will look like. So this is the Milky Way. We see it's a disk structure. This shows the stars. The Earth and Sun will be about this far out, sort of medium distance out from the center. I'll set the simulation going. Note the time scales, billions of years in the lower left. So we have the Milky Way serenely rotating, not much going on apart from its rotation. there it is. That's what it's doing now. But then enter stage right, the Andromeda spiral. It's coming directly for the Milky Way. It's falling, they're falling towards each other. And you see the time scales, we're now 3 billion years in. And eventually they're going to merge together. So this is you see the first pass, the disks get destroyed, get quite a mess and get tidal tails. And then they come back together and they merge. And actually what you end up with is something that looks like an elliptical galaxy. So we think through this merger with Andromeda, the Milky Way will eventually look like, the remnant of that will look like an elliptical galaxy. So I've got another view, there's an artist's impression here of what this would look like from Earth. So we have the plane of the Milky Way. Andromeda is actually surprisingly close to the plane of the Milky Way in projection. You know, it's a long way away, but we see it close to the plane of Milky Way in projection. And if I set this going, this shows what we expect to see billions of years again, coming towards us, Andromeda. I'm going to get a fantastic view. Everything gets messed up by the merger. And eventually we find ourselves living on the outskirts of a giant elliptical galaxy. So we have a very different view to that we have now of the Milky Way in about 7 billion years' time. An important thing is, though, as part of this merger, gas will flow towards the nucleus, the remnant nucleus, and we're likely to see a quasar. And that quasar, as I showed you in the simulation earlier, which showed the gas and dust, because it's so powerful, it's got so much radiation, it drives winds, will blast the remaining gas up the Milky Way. And that would be really the death of the Milky Way in terms of its star formation. So although we don't have to worry about quasars now, in the future, they're likely to be an important part of the evolution of the Milky Way. So to end close to where I started, the reason we classify galaxies to understand how they evolve and how they form and that sort of thing. And one of the things we know now from observations over the last 30 years or so, that one of the things that happens in terms of evolution is that spiral galaxies are transformed into elliptical galaxies by merger. So we take galaxies like the Milky Way, they merge together and form elliptical. It's not the only evolutionary process, but it's an important one. And as part of that, quasars are triggered, and they play a really important role in galaxy evolution because they're not only triggered in the mergers, but they drive these massive outflows that halt the star formation. So just to conclude, there's now convincing observational evidence from all sorts of different directions that most large galaxies contain supermassive black holes in their centers, including the Milky Way. But most of these supermassive black holes are in hibernation because they're not currently accreting sufficient material to appear bright. We don't get this conversion of gravitational energy into heat and light, so we don't see the active nucleus. But quasars are triggered when galaxies merge together, and large masses of gas are driven towards the centers of the galaxies where the black holes are, and we get this conversion of gravitational energy into heat and light. And so we see quasars, and those quasars then drive the remaining gas out of the galaxies. So they have a large impact on the evolution of galaxies. Okay, that's it. That's all I wanted to say. Thank you very much.
Thank you, Clive. That was really good. And we have some questions coming in. So
hey, good.
You've got a few minutes. First one from, and just to say to people as well, you can ask questions either on Zoom, or you can, if you're watching on YouTube, you can put them in the comments on YouTube and I'll pick them up from there. First question from Darryl Dobbs. He says, the Event Horizon Telescope, which is that extraordinary VLBI telescope that got this amazing image, he says the team there recently announced magnetic fields forcing back the gas from a black hole, and do you think this is a typical thing or unusual?
Yeah, so I think magnetic fields are really important. That actually talked about jets from objects like Cygnus A, and we believe to generate the jets, you need to have magnetic fields as well as a black hole. So the typical model is that you have a spinning black hole, it's threaded through with a magnetic field, which also threads through the accretion disk. And the spin of the black hole winds up the field lines, and when particles get tangled up in that, they get shot out of the center of the galaxy, and that's what we see as a jet. And M87, we know that it's got large-scale jets, and we believe that that's what's happening. So I think that magnetic fields are very important in the vicinities of black hole and their accretion disks. I must admit, I haven't read this article in detail, so I don't know what it means by forcing the material out. I'm not quite sure about that. But certainly we think these magnetic fields and spinning black holes could generate the jets. Okay.
Good. Adam Fairhead asks, do we think that some or all of ellipticals are formed from mergers?
Yes, as I think I said towards the end there, we think that, certainly some, perhaps the less massive ones in the local universe have been formed by mergers, such as the ones I showed between two spiral galaxies. And even at high redshift, more massive ones, mergers could be important. So we think that certainly the lower mass ones are probably formed by mergers. And that process is actually happening in the local universe, where we see these, things like the antennae. The antennae will eventually look like an elliptical galaxy. So we think that's a very important evolutionary direction.
Mm-hmm. Yeah. Okay, I'll ask a question as well whilst we're waiting to see if anyone else has got any. So most large galaxies, you say, have got supermassive black holes at the center, but they're kind of hibernating. Does that have any impact on the potential development of life in galaxies? Does it? I mean, for instance, in active galaxies, what would the center of the galaxy look like? Would it be kind of sterilizing from the kind of distance that we are from the center of the galaxy, or what kind of radiation?
Yeah, I think in terms of the light, okay, so you can work out that if a quasar was triggered in the center of the Milky Way and all the gas and dust was swept away, so we had a clear view, I think it would be about -13 visual magnitude. So it would be not quite as bright as a full moon, but it would be brighter than Venus. Mm-hmm. So it wouldn't be, it wouldn't be so dazzling, the optical radiation, but I think the X-rays and the higher energy radiation generated by the quasar could have an effect even kiloparsecs away where we are in the Milky Way. And of course, if you're close to the center, then it's likely to have a very major effect. In fact, there is evidence that although it hasn't been a quasar, there is evidence now that the Milky Way was an active galaxy, like a Cepheid, lower luminosity active galaxy, a couple of hundred mega years ago.
Oh, that recently.
Yeah, and I've actually got. Can I show a slide?
Sure.
Yeah, see if I can find the right. I'm looking through all my slides here. Oh yeah. So, whoops, I've gone out of the presentation mode. Hang on, take me a while to get back. Just bear with me a second.
No worries.
Quick recap of my talk. Yeah, okay. So just find the right one. Yep, sorry, that's it. Yeah, so what this shows is a combined gamma ray and X-ray image of the Milky Way. So in red, you see gamma rays, incredibly high energy radiation, 2 to 5 giga-electron volts, much more energetic than X-rays. In the disk, that's due to pulsars, small black holes, and relativistic particles. And then we also see X-rays, about 1 kilo-electron volt, they're in cyan. So we see the disk of the Milky Way, but above the center, we see this incredible bubble. So around the outside, we see the X-rays in cyan, but filled in, we see the gamma ray. And the gamma rays are generated by relativistic particles moving close to the speed of light, scattering photons, lower energy photons. And these are called the Fermi bubbles. And they're incredibly energetic if you work out the total energy associated with them. And it's believed that these are probably due to a phase of activity, AGN activity in the Milky Way a few billion years ago. So it's sort of Cepheid-like activity. It's a little bit controversial because we also have star formation in the Milky Way, which could generate this. But we think these Fermi bubbles are probably due to a recent phase of activity a few million years ago.
So,
but then that wouldn't have been enough to wipe away the disk of the Milky Way, and so we wouldn't have seen through directly to the AGN, and it probably wouldn't have had any effect on life on Earth, for example.
Okay, and it's not something that we could detect in geology on Earth.
No, I mean maybe. Yeah, no, we couldn't. No.
Yeah. Okay.
I don't think we could.
Okay, we've got a few more questions come in. So one from Peter Jennings. He says, do you feel that the same basic principles will apply in the same outcomes, i.e. creating an elliptical galaxy, if two barred spiral galaxies collide, merge, or if a barred spiral and a conventional spiral merge, i.e. does everything end up as an elliptical?
Yeah, I think they would, because I think you get the same general things going on whether the galaxy is barred or not. In fact, bars may be responsible themselves. You know, you just take a barred spiral galaxy, and we believe that if we could see it clearly, our own Milky Way is a barred spiral galaxy. They lead to radial gas flows towards the nucleus, and bars could probably generate a CFUT. They probably wouldn't be able to generate a quasar. So, you know, a barred spiral galaxy by itself without merging might have some activity due to the radial gas motions that push the gas towards the center. But in terms of a merger, I don't think it make much difference that whether it's barred or not. I still think we get a lot of gas being pushed towards the center, a lot of accretion, and, you know, that would generate a quasar. And, you know, you get this transformation because everything, the morphologies of the individual galaxies get completely messed up by the merger.
Yeah.
And you get the gas blasted out by the quasar. So I don't think it really matters whether it's a barred or a non-barred galaxy.
Okay, and just one final question then from Daryl Dobbs again. There seems to be a lack of intermediate mass black holes. The few that seem to have been found are in globular clusters. Do you think that these are dwarf galaxies stripped of their outer stars by the galaxy that they're orbiting?
Yeah, that's a possibility. I think, yeah, so if we look at our Milky Way, there's been evidence that globular clusters, so these are systems of stars at about 1 million solar masses. There's been some evidence, although controversial, that they contain black holes that could have a mass of, you know, 10 to the 3, 1,000 to 10,000 solar masses. But it's a bit controversial. And those globular clusters, one of them's Omega Cen, which you may, you know, some of you, if you do observations, may have seen. Isn't that one visible with the naked eye? I can't remember.
It's the brightest globular cluster in the sky. Yeah, it's really spectacular. That's
thought to be the strip core of a galaxy that's merging with the Milky Way. Mm-hmm. So yeah, so if that really does have an intermediate mass black hole in it, it's possible that it's come from a collision with a smaller galaxy, a dwarf galaxy. Mm-hmm. And in fact, there's a lot of work going on at the moment looking at isolated dwarf galaxies before they merge with a larger galaxy. And there's increasing evidence being found actually for black holes in dwarf galaxies with masses of about 10,000 to 100,000 solar masses. So we're beginning to fill in that mass range. It's true that there's not so far too much evidence for the intermediate mass black holes, but we're getting increasing evidence.
And that would be an observational bias more than anything else.
Yeah, it's just difficult because they're less massive. They're smaller, and you know, they have less effect, less easy to find, I'd say.
Okay, so I think that's all the questions. So thank you very much for spending your afternoon talking to us about it. Really interesting subject as always, and hopefully we can have you back to the BAA again sometime in the future. So thank you very much.
Yeah, it's been a pleasure. Thank you very much.
Thank you.
Thank you. Okay, bye-bye.
Cheers, bye-bye. And goodbye, everyone. Hopefully it's as sunny and warm where you are as it is with me. So go outside and enjoy it.
Bye.
Okay, cheers. Bye-bye.
Bye.